This is 351 Lab 5 First Order Sensors by Garrett Schweitzer. This is my first circuit, and I'm outputting 5 volts from digital pin 5, and I'm reading in on analog 3 with the 10K resistor. This is my circuit with the 100 kilo ohm resistor. As you can see, it's going to do just like the 10 kilo ohm resistor, except a good bit slower. Looking at the MATLAB simulation, it makes sense. The response of the circuit is faster with a lower resistor. This is my Arduino code for the 10K resistor. So we are writing the pin low for 5 seconds to clear the capacitor, discharge that completely. We have this main timing loop here, so every 10 tau we can basically either write high or write low, depending on this toggle flag that I made here. And that's going to go on depending every 10 tau it'll either do high, or if that's the previous one that occurred, then it'll do low. And then down here, tau over 50, we're going to be outputting our readings for the input voltage and the output voltage depending on the state of the flag. And that'll be read by processing. Here is my Arduino code for the 100K resistor. As you'll be able to see, it's going much slower, going between high and low, but also the response. Here's my processing code. So the first thing I changed was my baud rate here, and then I moved down to make axes on the chart. So I used a for loop to create evenly spaced lines using the line tool. I made a nice little equation here that would evenly distribute 6 lines up to 5 volts, and then I manually created text labels using the text tool. Created the legend where you could see VC and VIN as dots there in their respective colors. Here's my processing code running with the 100 kilo ohm resistor. As you can see, much slower response as we found earlier. This is my data for my 10 kilo ohms, 100 kilo ohms, and the theoretical data provided. And my data closely resembles the theoretical, with the time response being much quicker for 10 kilo ohms, much like the theoretical data, and my time response being much slower for 100 K ohms. I was unable to film me using the thermistor test, but I did collect data using this setup. Cold water here, hot water in this big cup, and then putting the thermistor into it, and I'll show you the data next. Here's my Arduino code. So a couple things. I found the resistance to be 10,000 ohms. That's the resistor I used in the circuit because it's the same resistance as the internal resistance of the thermistor, which, because we're using a voltage divider, will maximize our output voltage. The time constant according to the datasheet is 15 seconds. The hot water was 45 C, cold water 17 C. And all I did was a straight collection. I outputted the full value of the voltage in, and then outputted V out, which is still out of 1023. It's not corrected to be voltage. Having increased the size of these graphs, you can really tell that because the hot water was so much hotter, the response was much quicker for the hot water compared to the response to the cold water, which was much more gradual because of that low temperature differential. But these are all in line with the time constant we would expect for this, being about 15 seconds. This is also quite in line with what we know about first order systems. There's a nice gradual curve up to where you should level off if the data wasn't a little noisy. It's better seen in the cooling graph. You pretty much level off once you reach this steady state here. There's no gyration or undulation or anything. Both are relatively steady.